Problem number 8. We're looking here to add or subtract. We're going to need to get a common denominator. The key always is to think in terms of factors. So when I look at part A, x cubed means x times x times x. Those are factors. X and the other one is its own factor. I'm missing a couple more x's here, and then I could turn it into x cubed. So this is going to become negative 1 over x cubed plus 5x squared over x cubed. Now that I have a common denominator, I can add those tops. It's just going to be negative 1 plus 5x squared. Those are not like terms, so the best I can do is just write it down. I think I'll put it in the more normal order. Or negative 1 plus 5x squared would have been fine. And then all over x cubed. 5x squared and 1 are not factors, and 5x squared minus 1 does not factor, so there's nothing else I can do here. Letter B. The first denominator is just a factor of x, the second one is a factor of y. Each one is missing the other, so I'll fix this one with a y, and I'll fix this one with an x. This becomes y over xy, and 5x over xy. The bottoms match, so I can go ahead and subtract. I have y minus 5x up top, and then xy on the bottom. The only way I could reduce is if y minus 5x was factorable, but it's not. I don't have a GCF. I have no way to factor that, which means those pieces aren't factors, and I cannot go any further. Letter C. X minus 2 is its own factor. It does not factor. X minus 4 is its own factor, which means this is very similar to letter B. Each piece is just missing the other factor. So this one is missing the x minus 4, which I can fix top to bottom, and this one is missing the x minus 2, which I can fix top to bottom. Now, parentheses on the top are not helping me any because those are the pieces that are about to get merged in. So let's get rid of those. X minus 4 times 1 is just x minus 4. The bottom, I have x minus 4, x minus 2. And then on the other one, let's see, 3 times x minus 2 would be 3x minus 6. And the bottom, x minus 4, x minus 2. The bottoms match, and so that means I can go ahead and add up the tops. So let's see, can we just do it all at once? X minus 4 plus 3x minus 6. So x plus 3x is going to make 4x. And negative 4 plus negative 6 is going to make minus 10. And the bottom stays the same. X minus 4, x minus 2. Can I simplify this? Only if that top part factors. Now I do see there is a common factor of 2 that I can pull out to the front. That would leave me with 2x minus 5. Unfortunately though, I don't have any 2x minus 5s down here on the bottom or any just plain factors of 2, which means I cannot go any further. This would be the final simplified answer. Problem number 9, we want to work out each expression by hand. Looks like a couple of quick pictures ought to do it here. In the first one, I just need to think about the trig values for pi over 4. Pi over 4 is 45 degrees, so it's this similar triangle we've drawn many times. Sine of pi over 4 is 1 over root 2. Normally we rationalize that. I don't think I need to here, because then I'm multiplying it by cosine pi over 4, which is also 1 over root 2. When I multiply across, I think the rationalization takes care of itself. 1 times 1 is 1, and root 2 times root 2 is just 2. And so here then is the final answer. Part B is similar. I'm just using pi over 6, so that's the 30, 60, 90 triangle. Let's see, 1, root 3, and 2. The sine ratio of pi over 6 is 1/2. The cosine ratio is root 3 over 2. And when I multiply across, I get root 3 on the top, and 2 times 2 is 4 on the bottom. And so there's that final answer. And then lastly, sine squared pi over 3. All that means is find sine of pi over 3 and then square it. So I guess a quick picture would be fine here. Pi over 3 is 60 degrees. That's this triangle, 1, root 3, and 2. The sine ratio for pi over 3 is root 3 over 2. Squaring that, let's see, I can just square the top and square the bottom. Root 3 times root 3 is 3, and 2 times 2 is 4. So final answer, 3/4. And then problem number 10, we're looking to simplify trig expressions again. Let's see, part A, I could switch cosecant squared over to sine, but since I have more cosecants, I'm actually thinking it's probably simpler to reciprocate the sine x to the bottom, turning it into a cosecant x. So I left the cosecant squared x up top where it was. I reciprocated the sine x, and now I have a common factor of cosecant x, leaving me with, after I cancel those out, just that single cosecant x up top. Here would be the final answer. Letter B, I think I'll do something similar. I guess it doesn't matter which one I reciprocate. I'll keep the cosine squared, and I'll reciprocate the secant squared to the bottom here, which becomes cosine squared. Well, anything divided by itself is just equal to 1. In other words, everybody cancels out. Cosine squared over cosine squared is just the number 1. Letter C, cotangent squared and cosecant squared, they're in that same Pythagorean identity. I just need to think about which one I need. Of course, the main one, sine squared x plus cosine squared x equals 1. Let me do some scratch work here. The one with cotangent, that's the one you get by dividing everybody through here by sine squared. I know that because cosine squared over sine squared makes cotangent squared. So if I work that one out, sine squared over sine squared is 1. Cosine over sine is cotangent, so that would be cotangent squared. And then 1 over sine is cosecant, so this would be cosecant squared. Can I make a cotangent squared minus a cosecant squared? Yes, I can do that as long as I move this piece to the left and this 1 over here to the right. And then this would say cotangent squared x minus cosecant squared x equals -1. Well, that's what I needed. Cotangent squared x minus cosecant squared x, according to what we just found, is equal to -1. Letter D, it looks like I have a FOIL problem here at the start. It's actually a pretty simple one because sine x times sine x would be sine squared x. But then the outer and the inner ones wipe each other out. The outer one is plus sine x, and then I get a minus sine x from the inner one, so those are gone. And then I just have -1 at the end. Now, sine squared x minus 1 makes me think Pythagorean identity. So let's take a look at that main Pythagorean identity again. Can I make a sine squared minus 1? Yes, if I move this 1 over here and move the cosine squared to the other side, then it will say sine squared x minus 1 is equal to negative cosine squared x. Well, that's exactly what I needed. I have sine squared x minus 1 in my problem, and we just discovered this is equal to negative cosine squared x, which would be the final answer. Letter E, I have two terms being added up on the top and then a single term on the bottom. Since I only have a single term on the bottom, one thing I could do here is just distribute this to both parts. In other words, this would become sine x over cosine x plus cosine x over cosine x. Well, each of these fractions then simplifies. Sine x over cosine x is just tangent x, and cosine x divided by cosine x is just 1. And so I end up here with tangent x plus 1. Finally, letter F, I have so many items here being multiplied, I think I would change over to sine and cosine and see if I get some cancellations. So I have the sine x, cotangent becomes cosine over sine from the quotient identity. Secant x is 1 over cosine, that's a reciprocal identity. And cosecant x is 1 over sine from the reciprocal identity. So do I have anything that cancels out? Let's see. Well, this sine x would get rid of this sine x, and this cosine x would get rid of this. And when I say get rid of course, really what we're doing is we're just dividing things out. I think when you put all this together, I end up with a 1 on the top and just a sine x on the bottom. 1 over sine x is equal to cosecant x. And so there would be the shortest, simplest way that I could write this answer.